We think scheduling tasks on just one computer is hard, but what happens when you have thousands of them, all trying to work together, but with nobody in charge? Well, that's where things get really interesting. Welcome to the chaotic and honestly fascinating world of distributed systems. So, how do you coordinate without a central brain? I mean, think about it like this. Imagine you're trying to get a group of friends to agree on a plan. The catch? You can only pass notes to each other. And some of those notes might show up late, or not at all. Oh, and some of your friends might just wander off in the middle of the conversation. How in the world do you make sure anything actually gets done right? And this really gets to the heart of the difference. On one side, you've got a single system. It's a place of perfect order, right? Everybody sees the same memory, everyone agrees on the time. It's like a dictatorship of truth. But then you look at a distributed system, and it's pure anarchy. There's no single source of truth, no shared clock, no shared memory, and absolutely no one in charge. And yet, somehow, these systems have to find a way to agree on what to do next. All right, so here's the plan for this explainer. First, we're going to dig into why having no boss is so ridiculously hard. Then we'll peel back the layers to find the real problem hidden under scheduling. After that, we'll look at the fundamental rules of the game, see how engineers actually build these things, explore the spectacular ways they can fail, and wrap it all up with the true cost of going big. Okay, let's dive right in. Section 1, when there is no boss. This is where we really have to face the music, the harsh, unavoidable realities that make distributed systems such a wild and fascinating challenge. And look, these aren't some weird edge cases we're talking about. This is the everyday weather in a distributed world. Messages are gonna be delayed. Individual machines, we call them nodes, they're gonna fail, while others just keep chugging along. Some messages, poof, they'll just vanish into the ether. Every machine's clock will slowly but surely drift out of sync. And the kicker? Every single node is making its own decisions, all based on the incomplete picture of the world it has at that moment. And this is the absolute core of the problem. Because of all that chaos we just talked about, you can never, ever assume that two different machines know the same thing at the same time. You just can't. And that one simple fact changes everything about how you have to design software. It forces you to build for disagreement and uncertainty right from the start. Okay, so let's move on and see where this leads. We started this whole thing talking about scheduling, right? Deciding which machine runs which task and when. But in a distributed system, that simple idea just explodes in complexity. The cost of just getting the machines to talk and coordinate, it completely blows away the cost of doing the actual work. It turns out scheduling isn't the real problem. It's just a symptom. The true bottleneck is actually one level deeper. So let me ask you this. Before a bunch of these nodes can even begin to decide who should run a task, what is the one thing they absolutely must be able to do first? What's the fundamental prerequisite for any kind of teamwork in a world built on uncertainty? And the answer is consensus. See, the real problem isn't scheduling at all. It's agreement. Consensus is just the fancy name for the process that lets a group of independent, unreliable computers all agree on one single value, one shared truth. It's the bedrock everything else is built on. And it's super important to remember. Consensus isn't about going fast. It's about being safe. So what do they actually need to agree on? Well, pretty much everything that matters. Like, who owns this specific task? In what exact order do we process these updates? What is the official state of the system right now? And hey, which one of us has failed and can't be trusted anymore? If you try to schedule anything without first getting consensus on these things, you're just asking for chaos, corrupted data, and wasted work. This brings us to a really crucial point, the rules of agreement. Because getting all these machines to agree, well, it doesn't come for free. There's a catch. In fact, there's a famous fundamental law in computer science that forces every single distributed system to make a really painful choice. So the first thing you might want is consistency. Think of this as the promise of a single unified truth. It means that when you ask for a piece of data, you either get the most recent, up to the millisecond version, or you get an error. Simple as that. All the nodes see the exact same data at the same time. Okay, the second thing you might want is availability. This is simpler. The system always gives you an answer. It never says, I can't do that right now. But there's a catch. The answer it gives you might be a tiny bit stale, a little out of date. It prioritizes just responding over making sure that response is perfectly up to date. And the third piece of the puzzle is partition tolerance. Now, this one isn't really a choice, it's just reality. It's acknowledging that the network connecting all your computers is not perfect. Messages will get lost, the network will partition, basically splitting your system into islands of nodes that can't talk to each other. You can't wish this away, it's just a fact of life for distributed systems. So here's the kicker. You can't have all three. That's the famous CAP theorem. And since we already established that network partitions are unavoidable, they're going to happen, you are forced to choose between the other two. When the network breaks, what do? Do you choose consistency, meaning you stop taking in new information to avoid confusion, but that might make you unavailable? Or do you choose availability, staying online and responsive, but risking that different parts of your system will have different versions of the truth? Every single distributed system has to pick its poison. There's just no perfect answer.
Okay, so given these insane trade-offs, how on earth do we actually build systems that work? Well, that brings us to section 4, how agreement actually works. We're shifting from the laws of physics to the actual engineering.
So, deep down, at the very heart of consensus, you'll find these brilliant algorithms, most famously Paxos and Raft. Paxos is the OG, the original. It's mathematically proven to be correct, but it's also legendary for being incredibly hard to wrap your head around. It puts safety above absolutely everything else. Then Raft came along later, and its main goal was just be understandable. It uses a really clear leader-based approach that makes it way easier for actual humans to build systems that work correctly.
And here's the thing, you have almost certainly used systems built on these ideas, probably without even knowing it. When Kubernetes decides which server should run your application, that's distributed scheduling, powered by consensus. When a job queue spreads work across a bunch of machines, consensus. When a system makes sure only one server is running a critical cron job, yep, that's consensus again. Tools like etcd or Zookeeper are the real-world versions of these algorithms, and they are the secret foundation that so much of modern cloud computing is built on.
And the pattern you see over and over is pretty simple. First, the nodes hold an election to agree on a single leader. Then, that leader decides what to do next. Let's run this task. The action gets executed. And finally, the result is copied to all the other nodes so everyone gets caught up on the new state of the world. Elect, decide, execute, replicate. It's like the heartbeat of a distributed system.
But what happens when this elegant little dance goes horribly wrong? That brings us to our next section, when agreement fails. Because let me tell you, the ways these systems can break are genuinely wild.
Yeah, these are the things that keep distributed systems engineers up at night. You can get something called a split brain. That's where a network failure tricks two different nodes into thinking they're the leader, and then they start making conflicting decisions. This can lead to the same critical job being run twice. Or a leader could die right after assigning a task but before telling anyone, creating an orphan task that's just running in the void, untracked. All of these roads lead to one place, a dangerously inconsistent system. And this requires the most important mental shift of all. On a single computer, a failure is an exception, it's a surprise. But in a distributed system, failure is the default state. It's normal. You have to design everything from the ground up with the absolute certainty that things are constantly breaking in weird ways. Your system's correctness depends entirely on its ability to survive failures, not on its ability to avoid them. And that brings us to our final section, the big takeaway. After all of this, the chaos, the trade-offs, the failures, what is the real lesson? Well, it's a huge shift in how you even think about coordination. Here it is. This is the key insight. In distributed systems, you don't coordinate machines. You coordinate beliefs. Your job isn't really to manage hardware. It's to manage what each individual isolated machine believes to be true. The entire challenge is getting all of those separate viewpoints to converge on one single shared belief about how the world works.
So let's just tie it all up in a bow. We started with a pretty simple goal, scheduling tasks. But we found out really fast that to schedule anything correctly, all the machines first need to agree on what's going on. And the only way to get that agreement in a world where things are always breaking is through that formal process we called consensus. And that leads to the final thought. Why? Why do we put ourselves through all this trouble? Why deal with network partitions and split brains and all of it? It's because we want to build systems that are bigger, more powerful, and more resilient than any one computer could ever hope to be. And all of that mind-bending complexity, the algorithms, the painful trade-offs, the whole field of study, that is simply the price we pay for scale.